OpenAI introduced a new open source Agents SDK, which is based upon 4 principles: agents, handoffs, guardrails, and tracing. In this video, we will take a look at how to get started, how to build systems with it, and look into the more fine details, how to build great agents with the SDK. So let's get started. Agents are becoming more and more popular in AI development. The reason is that they can better orchestrate tasks because of the built-in self-reflection mechanism. The way it works is they will give a response and check upon that response before handing it back to the user. If they think they can do a better job at giving a better answer, they will refine their previously given answer, leading to better end results. OpenAI already had the Swarm SDK, which was their previous solution for building agents, but it is now replaced by the OpenAI Agents SDK, which during the recording of this video is only available as a Python SDK, but a JavaScript SDK is already announced and will come later on. In this video, we will first take a look at the principles of the SDK. Then we will build our first system and then look at each of the principles in more detail and even show a way to add other vendors such as Gemini as the LLM that powers the agents in the SDK. So let's first take a look at the principles. The first one are agents, and to no one's surprise, they play a very crucial role in the entire system. They are responsible for making calls to the LLMs, which can be different ones depending on the agent, and they will give responses back to the user. For performing their tasks, they can use tools whenever they decide they need them. Another mechanism agents can use are handoffs, which means they hand one task off to another agent. And for that, it's recommended to use something like a triage agent that decides which agent is suitable to perform a certain task. One of the important safety mechanisms in the system are guardrails. They can again be part of an agent, and there are 2 possible ones: input and output guardrails, and we'll take a look at how each of them work later on in this video. But basically, it's just a way for the agent to check whether the input is something suitable or if the output is fine as it is. The last important principle are traces, which is very cool that this is a very prominent feature in the SDK, as it provides a way for us as developers to have an understanding in what the LLMs and the agent systems are actually doing, which tools they are using, which agents they're handing off to, and with that we can refine our systems, improve not only the developer experience, but also the quality of results in the end. So let's look at how to get started with building our first system now. We start off with a very simple system to understand the core principles. So let's jump directly into VS Code to look at this. I created a Python file here called first look, and we can now start to fill that up. But first, a disclaimer: we need to have an environment file that has an OpenAI API key as a secret stored, and the SDK will automatically detect this and use this API key. So inside the Python file, let's first import the agent object from the Agents SDK. With that, we can build our first agent, which will be a research agent. We can give it a name that is unique and identifies the agent itself. And then we will give it instructions, which we can otherwise think as system prompts. In this case, it's a very simple one, saying you are a helpful research assistant. But of course, the real power comes in when we use tools for this agent, and we can first select one of the built-in ones. And here we have the web search tool. There's also other ones, such as a file search tool, a computer use tool, and there might be others in the future, but these are the ones we're getting for now. So after importing that, we can use this tool here by calling and initializing it inside the tools parameter here. Now we need to run the agent, and for that we import the runner from the SDK, and then we can call it synchronously by handing it the research agent as the starting agent, and then adding a query to it. This can be dynamic, of course, but for simplicity we will just say something like "Are AI agents sentient or ready?" And then in the end we can print the result of the final output. So if we open up the terminal here and execute python firstlook.py, we can get the answer and can be relieved because it clearly states that AI agents are not sentient. Good news, we haven't created AGI just yet. So let's continue, maybe we'll get there. But let's say we want to have more than one agent. We have the research agent now, which is nice, but we want to have one more. And let's add a weather agent, which has the instructions of "You are a helpful weather assistant." We're not very creative with our instructions here, but it's just to get the point over. Now we want to give this a tool, but we don't have a built-in weather tool at our disposal, so we need to create our own tool. And this is also quite easy because for that we can just define a function. We call it getWeather with a string of the city, and we will return a string of the weather prediction. However, with that we can't just use it as a tool, but we need to do one more tweak here, and specifically we can import the function tool from the Agents SDK and then use it with a decorator to decorate the function and specify it as a function tool that an agent can then call. We will have a very complex logic inside of our getWeather function. Of course, we could also call an API or perform more complex logic there. But for simplicity, let's keep it simple and just give a string of "It's always sunny in the city we hand in." And then we can add this as a tool for the agent by simply handing the getWeather function inside the tools parameter. Now, we don't know which agent we need to call when running a query. So let's change that, because as I mentioned, we want to have a agent that is actually responsible of deciding which other agents to run. So let's create a triage agent and give it the instruction of "You decide which agent to hand off," and as the handoffs parameter for this agent, so they're not getting a tool but a handoff parameter. And for that we add both the weather agent we just created as well as the research agent we created earlier. Now when we run the runner, the difference now will be that instead of the research agent, we call the triage agent, which will then in turn hand over the work, depending on which query we're sending it, to the respective agent it figures out is the best one to solve. And here we are putting in a weather query. So let's run this as well. Let's again say we execute the program, and the result will be "In San Francisco, it's always sunny." So it's even not taking the pure output of the tool, but it's also putting a slight LLM spin to it. With that, we have created our first system. So now let's look into more detail how we can configure agents inside the SDK. Since agents are such a vital part of the SDK, let's take a closer look at how we can create them, what options we have, how complex we can get with them. But first, let's think again about what we need to create a basic agent. And first we can define a main function to run a system. Now we have done the synchronous way before, so let's also take a look at the asynchronous way, because it's probably more common in agent systems. And for that we need to import the Agents SDK, of course, again, and then we can create the research agent. And there's actually only two parameters we need to set. The first is the name, and then we need to give it the instructions. I already mentioned these are basically the system prompts. We can then again import the runner. We can say await rather than run. And instead of just handing it the agent, we can define it as the starting agent. And we can then put an input there. In this case, when did the Roman Empire really fall apart? And then print the final output of the result. And then we can say, if we are in the main loop, we import async IO and then run the main function asynchronously. This is how we can run the agent asynchronously. And now the agent can have more options, of course, for being created. And the first that we already saw is the tool. So we can add, for example, the web search tool to hand the agent as a way to research more information. But also we can define the model for the agent. And for that we have the usual options such as O1, O3 Mini, GPT 4.5, 4.0, 4.0 Mini. We can even use external tools, which we'll get to in a second. But for now we can see that we have the option to specify the model that each agent uses. So if we have models that are more suited to be using a reasoning model, we can use that, or lighter weight tasks can be handed to a 4.0 mini model, for example. So we have more options there, which is very convenient. The second mechanism we want to discuss is called context. And it basically gives us a way to provide the LLM with some context around the system that it works with. In our case, you want it to give the context of what a user is. And for that, we have the option to just create a data class. We call it user info. It can have a name and a UID or other parameters which we can add. And then we can create a function tool that, for example, fetches the user age. And for this, we hand in a wrapper, which is a run context wrapper, which has access to the user info object. And then inside we can say the user with the name specified in the context is 47 years old. We can then define the user info in the beginning and hand the user agent a user info context object so that it's aware of the context it's working in. And as a tool, we can give it the fetch user age function to detect the age of the user. And finally, we can, as context, add the user info that we have defined before. Now, what is important to mention is that this info will not be handed to the LLM as additional context. So it's not a way to add a RAG system into the agent, but only the agent itself can be aware of the context, and it needs to be the same for all the agents in that system. So if an agent will be triaging work to other agents, they need to share the same context object. There are other techniques for RAG systems, which we will also briefly discuss, but just be aware that this context object is just something to define that the agent gets some information about. Back to the next feature, which is structured outputs. It is a mechanism to tell an LLM to have a very specific output in a very specific format, which can be important for things like API calls, where we need to have a very specific set of parameters to call them. Or we can also have other examples for that. The Agents SDK comes with first-hand support for this, which makes it quite easy to do this. So for example, if we have a weather agent again that needs to get the weather for a certain location, we can specify how the output should look like. And we can use Pydantic to define a weather event which inherits from base model, and it has certain parameters such as a forecast, the temperature as a float, and the hourly temperature as a list of floats throughout the day, for example. And then we can very easily hand this to the agent to get a structured output in the end by simply specifying the output type to be of weather event. I think it's very convenient to have such a simple support for such a very basic and important feature. The last example I want to take a look at are handoffs. And here we have defined a shopping agent and a refund agent. And as I showed before, we can now define a triage agent that takes the shopping agent and the refund agent as an array to the handoffs parameter, so it will decide which agent to work with. And for that we can give it instructions, but we're not limited to a single string for instructions, but we can also use multiple ones to give the agent more information how to handle certain tasks. And while taking a look at this, I want to quickly mention that we have different options to hand specific information to an agent or a system, because this is what a RAG system will need to inject the custom information that we want to give it about our systems. So one example that we already saw is that we can hand them in via the instructions that I just showed you. This can also contain information that we want to give it. The other option is to hand it to the system in the runner, so we can add additional information there as context. The third option is to expose it via function calls. So if an agent might think it requires more information to solve a certain task, we can give it a tool to, for example, read in our database to provide specific information to an agent. And the last option is to simply have something like a research tool or a research agent that uses web search or file search to perform the task of acquiring the necessary knowledge. But with that, we have covered agents quite a bit. So I want to jump to the next topic, which is going to be integrating an external LLM provider. Before we start the implementation, let's quickly discuss why we actually want to do this. Because OpenAI provides a lot of models for us, and I already showed you a list of them. But still, we might want to use other models from other providers, such as Google with Gemini, Anthropic with Claude, DeepSeek, or even any other provider. The only necessity that we have is that it needs a OpenAI compatible endpoint. But by now this has become more or less of an industry standard, so it's rather common to have that available. We can even use local models, and I will explain how this works. But for now, let's take a look at the example of using Gemini. And for that, we jump back into VS Code. And before starting the implementation, I want to mention that there are multiple opportunities to do that. We can either set the entire model family to be something different. We can set the models that we use in a certain run, so with the runner, to be of a specific provider. But in our case, we want to use the, in my eyes, most practical one by specifying the model for a certain agent. And with that, we can mix things up quite freely. So first of all, we have a system here that uses a weather agent. We use that agent to get a call and print out the final result. So it's a rather simple system, such as the ones we've built before. But now we want to switch things up by not using an OpenAI model, but a different one. The first thing we do is we define the base URL where the model that you want to take a look at lives at. In our case, for Gemini, this will be this URL. In other cases, for example, if you use a local model, it can also be localhost something. But for this, we have the base URL. And since we're using another provider, we also need to import an API key for this. And this one we have defined in the environment file. So from there, we can import the Google API key and have that available here. Now, one important thing is that we need to set tracing to be disabled. Not always, but if we replace OpenAI in general, we should set this to be disabled, because otherwise we'll get an error since it tries to connect to the OpenAI platform via the API key. And if that's not defined, we will see an error. So in our case, we set tracing to be disabled. If you still want to use the dashboard with the entire tracing that they offer, then feel free to keep this active. The next step is to import the async OpenAI client and initialize it using the base URL as well as the API key. With that, we already have a client available that connects to this URL. And the last step is to import the OpenAI chat completions model. This is still the older version, and they recommend, if possible, to use their new responses API. But for this one, we need to use the chat completions model, and we can initialize this using a specific model from the Gemini family. In our case, for example, we can use 2.0 Flash. And then as the OpenAI client, we can use client. The OpenAI here specifically only targets OpenAI compatible endpoints, as I've explained before. So with that, we have a model available, and we can plug that model into our agent. And with that, it will completely use the Gemini model and not call anything from OpenAI, especially if you have the tracing to be disabled, as I said before. I think it's a very promising signal from OpenAI that they have made it so easy to integrate other vendors into their SDK. In our case, Gemini, but as I mentioned, we can also include any other ones. So I think it's very cool that this is so simple. But now I think we have covered agents quite a bit. So let's look at another feature that we have in the system, which is guardrails enable us to perform checks or validate user input. They run in parallel to agents. And let's assume we have an expensive task, for example, a support request that you want to send to a more complex model. But first, we want to validate that this request is actually a valid request and not just somebody asking for their homework. So for that, we could implement an input guardrail that first validates that it's a valid request and then sends it to the more complex model. For the validation of the input, we could use a lighter weight model that might be sufficient to detect a malicious intent, and then we can save money by simply not allowing it to access the more complex one. So let's look at an example how we could implement this. We have a very basic agent system running here that has a customer support agent, and we get a request saying, hello, can you help me solve for this equation? So as we have discussed, this is probably one we don't want to really answer, because this is just somebody trying to get their homework solved, which is not the purpose of the support agent. Now, the important principle that we want to introduce here is called tripwires. And the idea is that if an agent is set to perform a task that it should not do, so if the input guardrail is triggered, it will raise a tripwire exception, and with that stop its execution and return immediately. So let's first of all integrate this tripwire exception into the runner, and then we will do the implementation for the agent. So we import the input guardrail tripwire triggered, and there's also an output equivalent of that we will see in a second. And then we say we first want to wrap this with a try statement, and then we catch the exception of input guardrail tripwire triggered and print math homework guardrail triggered. And we can even add a print statement here, which we should never run into. Since this is now configured, we can actually do the implementation of the guardrail itself. For that, we first define a type. We use Pydantic for that. We've done that before. It's called math homework output, and we say we want to know if this is math homework, yes or no, and even get a reasoning for that in form of a string. We can then define a guardrail agent that specifically detects if this is just somebody asking you to do their homework. And we want to get the output type that we just defined for it. So we can then add an input guardrail, which is a decorator for a function that we can define. We call it math guardrail. and it will have a few parameters here. It will return a guardrail function output. We'll get the input, which is a run context wrapper, and we don't specify any context here. There is an agent and an input string, or it can even be a list of response input items. And as I said, it returns a guardrail function output. So we use a runner to run the guardrail agent with the input, and we even add the context that we receive. Then we return a guardrail function output object, which says the output info is the final output as the result we're getting from the runner. This is optional, we don't necessarily need this, but we can add some additional information. And the important parameter we need here is tripwire triggered, because here we can extract the is math homework from the final output. So if this is true, it will trigger the exception that we then catch here. So the last step we need to take is to put this input guardrail that we have defined inside the input guardrails parameter of the agent that we're running, that we're doing here. And with that, if we run the agent here, it will detect that this is a math homework request. The input guardrail tripwire triggered exception will be triggered, and we will catch this. And with that, we will save our more expensive model from even executing. So this is the input example, and the output example is very similar. So I'll just quickly go over it. We simply need to change the tool decorator to be an output guardrail. The rest is basically the same. We have the guardrail agent as well. It's checking for something different here, but the idea is the same. And here we simply want to have the output guardrails with the same tool, and everything else is running the same, except that we are listening for the output guardrail tripwire triggered exception instead. So with that, we know how to save execution of more complex tasks. We can check and validate the input as well as the output. So this is how guardrails work in the Agents SDK. The last important aspect that we want to take a look at is tracing. And I think it's remarkable that we have such a great support for tracing out of the box in the Agents SDK. And before I talk too much, let's directly take a look at how this is implemented. And we can go to platform.openai.com/traces to take a look here. And you see I have all the agent workflows that I have run so far. And if I want to see the execution time, I'm getting that. I'm getting the dates whenever they were run. I can do searches for that. But also I can click on one of the executions and I see a more detailed breakdown of how long each of the steps took. I can see which agent ran first. In this case, it was the triage agent. Upon clicking, we can take a look which handoffs it has configured. We can take a look at the responses, at the instructions, at the input or the query it got. Then we take a look at the handoff it did. We can take a look at the weather agent. We can also look at other runs. And for example, here we have a similar workflow. We can even see that a tool was called. We can see the function call happening with the parameters. We can see the output. We can see how long it took. So there's a ton of useful information for us available without configuring anything. Of course, we can also go into more details and configure tracing on our own. There is excessive documentation for this, but I want to quickly add that there is also support for external tracing processors such as Langsmith or Braintrust or AgentOps and others. So I think it's again nice to see that OpenAI are not only integrating this very well into the system out of the box, but they're also opening up the system to make it easy to plug in the provider that you might be using for tracing already, and making it easy to switch to the SDK, even if you rely on these services. So to sum things up, we think the OpenAI Agents SDK is a really intuitive framework that makes it very easy and straightforward to get started with agent implementations. There are a lot of options to configure agents in the way that we want, either through defining tools, handoffs, and even more complex things such as guardrails for validating input. And also the support for tracing features is really nice to see. Also, it's very cool to see that they have used an open source approach for implementing the SDK. And also they make it really easy to integrate external providers such as Gemini, Claude, whatever, into the system. And they do a similar approach for tracing. So it's not a closed system where you need to rely on one provider to rule it all. So for us, it's a promising SDK. We really enjoyed working with it. And we're curious to see once the JavaScript SDK is released and new features are being dropped. And we will definitely take a look at this once it's out. What do you think of the SDK? Have you tried it already, or are you trying it now after seeing this video? Feel free to add your thoughts in the comments. If you enjoyed the video, give it a like and subscribe to our channel. And we'll see you in the next one. Have a great day. Bye.